Okay, for chapter 12, we're going to get into rates of reactions, which describes how fast they happen and how they change over time. Generically, we just think about, reactants go down and products go up, and we measure those changes and how fast the reactants change into products, and that's chemical kinetics. Some learning objectives. And then here's a graph, and we can see over time, I've got this equation here, 2 NO2s decomposes into 2 nitrogen monoxides and oxygen gas. And we can see that the NO2 is my reactant, and it starts at a high concentration and it goes down over time, but it starts to slow down. And then my 2 NOs, they get a little bit higher, they move really fast, they change a lot at the beginning, and then they start to slow down. And then the oxygen changes really fast and slows down a little bit differently. So the direction here, positive and negative, tells me reactants and products and which way the reaction's going, but as well as coefficients. This tells me that the 2 NOs, for every 2 of those that I lose, I'm going to gain 2 nitrogen monoxides. So you see the slopes here is what the rate is. The slopes of those are identical, they're just going different directions. And then the oxygen has a coefficient of 1. So the coefficient is, this graph is going to change at half the rate of the others, and the slopes are about half of the other slopes. But you can even see as the concentrations change over time, it starts to slow down. That's because there's less and less of the stuff to react, the collisions are happening less frequently, and the reaction actually starts to slow down. So here is some data for a hydrogen reaction. Hydrogen and oxygen combustion turns into water. And we plot this over time, and we say, okay, at these different intervals, what are the concentrations of all of my different species? The hydrogen and oxygen are going down, and the water is going up. So we can see here that they change at a ratio of 2 to 1 to 2. And we can take any time interval here and find the rate. What is the change of the hydrogen over a given time interval? Okay, so the questions that go with this data are actually on the next slide. I can't flip back and forth between them very linearly. So let me just read them here. It says, based on the coefficients of the chemical equation, what is the rate of oxygen between 0.004 and 0.008? Okay, so if we want the rate of the oxygen, we're going to take the oxygen data from 0.004 to 0.008, and oxygen is going to go from there to there. So let's take a look and see what that says. Rate is change in concentration over time. So concentration is 0.0675. I need to redo that. The change in concentration is always going to be final minus initial. So if we get the oxygen data, it's 0.0612, the final oxygen at the later time, minus 0.0675 over the change in time, and that is going to be 0.008 minus 0.004. Okay, and the way that we're going to define this for oxygen, the rate of oxygen, since it's a reactant, it's going to be the negative, we say it's decreasing, so that negative sign is going to be a direction, concentration over time. The rate is going to come out to be positive, because if we put that negative sign in there, but that's going to give us a number for oxygen that rates are always generally recorded positive. We just say the negative means decreasing, the positive is increasing, depending on which way the reaction is going. So we work that out and we get the rate of oxygen is going to be 1.58 with sig figs. And this is molarity and this is time. So I'm at molarity per second. And sometimes we'll say it was usually written inverse second, but you can put it in the denominator too if you wanted to. Could just say molarity per second, moles per liter per second. That is the rate of disappearance of oxygen. So if you ever see a negative sign with the rate, just know that that just means it's going down. That's totally possible for that to happen that way. The second question that goes with that is going to be, what is the rate of water production during that same time? Well, if I look back at the balanced equation, oxygen and water coefficients, the water is 2 to 1. So if my oxygen equation is this, and it's going down, my water is going to be double. My water is going to appear twice as fast. Okay, and the water is appearing, so that's definitely going to be a positive value. So here's part A. Part B is the water. It's just going to be times 2. The water is going to be 3.1 moles per liter per second. Maybe 3.2 with sig figs, depending on where you rounded. Third question, it says, use concentration versus time data to prove your answers. Well, that's actually what we did up here. Now we could just do that for the water. So in that same interval, now if we went back and looked at the water data, we could say 0.0375 minus changing water 0.0250 over the change in time 0.008 minus 0.004. And that should come out to be that 3.1. We did it this way just by looking at the coefficients. The water is double. We did it this way by doing the definition of a rate, which is the change in concentration of water over the change in time. So really simple definition for a rate, concentration over time. Later in the chapter, out of context, sometimes it's actually kind of hard to remember that one. So here are the questions that we just went through. And here's another example. Here you've got a generic equation. It says, what are the coefficients? If we know the rates of all 4 substances, we know some of them here are negatively defined as reactants. They're going to be going down. And these are positive. Those are my products, so that fits in there. What are the coefficients? Now, we have to have a known, otherwise we can just get a ratio, but they might not be the right coefficients. They're telling us that A is 2. So the value of A is 2, and we know that that's 0.05 moles per liter per second. So we just compare everything to A. B is actually triple that value. So my coefficient for B has to be 3 times bigger. So that's going to be a coefficient of 6. That is a really bad 6. There we go. Coefficient of 6. Okay. C is actually 0.5. C is actually 3/2 of A. It's a little bit bigger. It's not double. It's less than double. It's just another half larger. So if my coefficient for A is 2, my coefficient for C is going to be 3. The other way you could do it is do D first. D is half of A. So D is my coefficient of 1. And then you can kind of see that D to C is triple, so that's 3. You can do it that way too if you don't like fractions. But just simple rate data, we can see relatively how each concentration is going to change compared to one of the other rates of the substances. So we can define this, so we can measure each thing, we can graph each species in the equation, A, B, C, or D, reactants or products, doesn't matter what they are, but we're going to dive into a little bit more complicated rate data, just looking at one of them at a time. And when we do one at a time, it's called a rate law. So we're going to look at rate laws here and define for only one substance. And we get this generic construct here, rate equals Ka to the n power. A is a concentration, a molarity of something, that's what those brackets mean. And the concentrations, the speeds, the rates will change as a function of the concentration by an exponential value. Okay? It's called the rate order. How does the concentration affect the speed? We can get some simple ones we're going to look at are 0, first, and second order. We're going to do some simple calculus with these numbers later, so we're going to stick to clean numbers, 0, first, or second order. But they can be a lot more complicated. They can be fractions. We might see that occasionally, but later in the harder versions, we're going to stick with whole numbers. So how would the rate change if n equals 0? Well, anything to the 0 power is 1. So if that term just went away and I had the rate is just equal now to k, well, the rate doesn't change for the concentration. There is no concentration in this equation anymore. That's totally gone. If we said, what if it was first order? Okay, a to the first. Okay, so now my rate law is rate equals k a to the first. Well, that's a direct relationship. A is proportional to the rate. If A doubles, the rate will double. If A triples, the rate will triple. And what if my exponent were a 2? A to the second power. That one should be outside up there, sorry. Well, now my rate law says rate equals K. K is a constant. It'll be there all the time. Squared. Now it's a squared relationship. That means when my concentration doubles, we square that, my rate will change by 4. It'll be an exponential change. So we want to see how these are related. If they're not related, it means we have a 0 order reaction. If it's a linear relationship, then we have a first order reaction. And if it's a squared relationship, that means we have a second order reaction. So these exponents are going to tell us how that rate and time data changes as a function of one another. So simple example here. How does rate change? How does the rate of decomposition of A change as we change the concentration? A couple of things here. This is an initial molarity. This is looking at 3 different trials. Okay. I don't know what just happened there. Okay. This is trial 1, trial 2, and trial 3. Okay. These are 3 different trials that we measure the rates for 3 different trials at the very beginning of a reaction. So we can look at this and make some comparisons. And we say, okay, let's compare trial 1 to trial 2. What happened to my concentration? It doubled. What happened to my rate? Okay, now this is a little harder to see because the exponent changed. But imagine if this was 2.9 times 10 to the 29 times 10 to the negative 4th. So we can keep the exponents the same. Well, 7.2 raised to 29, that shows me that that's going to be 4 times bigger. So what order is going to affect that? What order says when my concentration doubles, my rate quadruples? Well, that's a second order equation. Okay? So my rate law here is going to be the rate equals K A squared. Okay, we just visually looked at this and said, double that, what happens here? It quadruples. There's a mathematical way to do it as well. Let's take a look. If we did, and this is a much longer way. Very rarely will you be required to do this. But if we just said, okay, the rate of trial 2 is equal to K, A, and we do not know the molarity, or we do not know the order. So we'll call that X. That's going to be, we're going to make a comparison to the rate of number 1, K, and it's the same order to the X. They will have the same exponent. Now the numbers changed, and you'll notice that the K's cancel out. So rate 2 over rate 1, that gives me 2.9 times 10 to the negative third over 7.2 times 10 to the negative fourth equals, my concentration in trial 2 was 0.7 to the x power over 0.35 to the x power. And if we simplify that, we have 4 equals 2 to the x power. Well, clearly x is squared. So this is an important way to look at this over here algebraically. We're going to compare two trials, 2 to 1. We usually put the bigger one on top. That gives us whole numbers. And we say, okay, the rates are going to cancel out. As the rate doubles or quadruples, my reaction doubles. We can do it qualitatively just by observations, or we can do it algebraically by comparing the rate law of number 1 over the rate law of number 2. The only unknown is the order, because the constant is cancel out. So we compare those rate laws and just solve for the order algebraically. Okay. But now that we know that the rate law is up here, it's Ka squared. We found the order is 2. Now we need to use any data. We can use any trial, 1, 2, or 3, and solve for K. So if we just plug that in, trial 1 is usually, people like to go to the first one. 7.2 times 10 to the negative fourth, that's the rate, equals K, now K is my unknown, times 0.35 squared. And the only unknown is K. K comes out to be 0.00588. Okay. Now, what are the units on K? Every problem has a unique units on K. Okay. So if we look at this, we see the units on rate are moles per liter per second. And we want to look at them as moles per liter per second. Change in concentration over time. So K is its own thing. And then molarity over here is still moles per liter squared. So moles squared over liter squared. Okay. If we divide by moles per liter squared, so invert it and move it to the other side, we isolate K, we will actually get liters per mole seconds. So those are going to be my units on K, which is very strange. 0.00588 liters per mole second. Okay. Last question. How does the rate of decomposition change as we change A? And we've already said that that is a squared relationship. So we bring all this back down here. Okay. And we just used that from the first two trials. We doubled that, and this one got quadrupled. We can actually see it with the other trials too. We triple this here from trial 1 to trial 3, triple that, and then this is actually going to go times 9, 3 squared. So 7.2 times 9 is going to give me that 6.45 times 10 to the negative third. So we know indeed that this is a squared relationship. The rate law is Ka squared. And we're going to use that information to solve for K, and then we can apply it in other scenarios. For this example, we have two different reactants. We have A plus 2B turns into products. And remember, we don't really care what the products are because our rate laws, we usually define them by the reactants because we have control of that, so that's our experimental data. Now, this is a really important question here. It says, what substance are the initial rates measuring? Every data set is defined by one or the other reactants, not both. We saw a couple slides ago how we can use these coefficients 2 to 1 to relate them to one another, but this data set is measuring the initial rate of A. So that's going to be incredibly important, okay? So the following question here is really simple, but out of context, we miss it. What is the initial rate of B in experiment 2? Well, we look at experiment 2, and it's 4.59 times 10 to the negative fourth. And that's the rate of A in experiment 2. The rate of B is going to be double the rate of A. So double this will be the initial rate of B. And we can't lose sight of that. Every data set you're going to see in this chapter will be defined, and it's here in the text, and it's up here in the rate law. All of this data is pertaining to A only. But the balanced equation can let me relate it to anything if I just use the coefficients. So the second part of this then is going to be to find the rate law. So to find the rate law with two variables, now we need to isolate them one at a time. And if we look at experiment 1 to 2, we can see that A is not changing. So any change in my rate law is going to be as an effect of B. Okay, so we look at this just like we did before, and we say, okay, B is tripling here, and my rate is tripling also. Therefore, my rate law so far, again, we get this generic, the rate is equal to K, A to the something, B to the something else. We're just looking for those coefficients. And then B we just found as first order. Okay? So B is going to be a first order reaction because the rate triples as B triples. Now in order to find A, we need to look at trials here, 1 and 3, because as B is constant, A is going to double, and then B is going to go up by 4 for A going by double. So that's a second order reaction. So A squared B to the first. That's my rate law for this reaction. Now we can do that, again, we want to be able to do that algebraically as well, because sometimes it's not as simple as just looking at that data set. 90% of the time it is, but sometimes it's not. So generically we said, if we just did trials 1 and 2 again for B, I could say the rate of, we're looking at trials 1 and 2 again. I'll take 2 over 1 because that's the bigger one. The rate of trial 2 is K, A to the X of trial 2, B to the Y of trial 2, over the rate of trial 1. K is the same. A of trial 1 to the X power, and B of trial 1 to the Y power. So when we do it this way, we just kind of take two generic rate laws, one over the other. The K's will cancel out. And since A is held constant in trials 1 and 2, A cancels out as well. So we're left with rate 2 over rate 1, which is 4.59 times 10 to the minus fourth over 1.53 times 10 to the minus fourth equals B is going to be 0.3 in trial 2 to the Y power, and that is going to be 0.1 to the Y power. And that's going to simplify to, let's move it up here so we can. That's going to simplify to 3 equals 3 to the Y power. Y is 1, first order. Now we knew that because we can just see the direct relationship. One triples, the other triples. We can see that in the data set, but they're not always so simple. So we want to understand that algebraic process also. All right, solve for K. Any data set works. So my rate law again equals K. We said A squared B to the first. That's my rate law. So we can take any of those and plug in the data to solve for k. So first trial works just as good as any others. So in the very first trial, the rate was 1.53 times 10 to the negative fourth equals k. A was 0.1 squared, and then B was also 0.1 for this trial. Coincidence, not necessarily always the case. So we solve for k. And k comes out to be 0.153. Again, let's do the units for the k. I'll do that up in blue. The rate law is moles per liter per second. That's the rate. And then we have k. And then since this is molarity squared and molarity to the first, we can just generically say that that's moles to the third over liters to the third. When we simplify that, just algebraically solving for k, multiply both sides by liters cubed, those cancel out. Divide both sides by moles cubed, those cancel out. And then we do that over here as well. Cubed, sorry. And one of those will cancel out to leave squared. One of the liters will cancel out, so it's inverse. We're going to get liters squared over moles squared per second. And that seconds is still in the denominator. So we need the units on k. It's different for every problem. But there's a little trick. There's a pattern here if we're paying attention. It has to do with the overall order of the reaction. Since my A is second order and B is first order, we say the reaction order overall is 3. It's a total order. Since rates are always in moles per liter, and my reaction order, in this case, is moles cubed per liters cubed, we need our rate law units to cancel out all of that reaction order, leaving moles per liter. So in order to cancel out those moles per liter, and I'll work through that here in a moment, we need to invert it, liters per mole, and we need one less than the reaction order. And I'll revisit that at the very, very end of this lesson. Let's do one more rate law first. Okay, so here's one where we have 3 different reactants. C, D, and E, and we have unknown orders, coefficients 2 to 1 to 1. That doesn't really matter except for how the rate law is defined. And this rate law is defined according to C. So if we wanted these rate data value points for D or E, we would have to look at the coefficients and change this column only accordingly. But that is the rate of C, based on these initial concentrations of 5 different reactions. So what's the rate law? Well, let's take a look at our trials. Now, in order to isolate these variables, we need to find each variable changing while the other 2 are held constant. So let's go ahead and do the most difficult one first. We'll just do them in order C, D, and E. C happens to be the hardest one. If I look at trials 1 and 5, D and E are held constant. So I can look at the rate law from here to here and compare it to here to here. Okay, so that lets me kind of ignore D and E and look only at C and the rate law. All right, so let's compare those. All right, so 0.4 to 0.1. Now they're out of order, and sometimes they are. If C here is getting 4 times bigger, going from 5 to 1, here it's only getting 2 times bigger. Now some of you can see that mathematically, and some of you are going to struggle with that. So let's look at it algebraically, because that's kind of tricky. So what we need to do is we need to take, we're going to take the bigger number on top here. We're going to say rate 1 over rate 5. We're going to compare those two rate laws. Now, K's are going to cancel out, D's are going to cancel out, E's are going to cancel out, so I can just look at the concentration of C in trial 1 to the x power over the concentration of C in trial 5 to the x power, and just get that exponent. So the rate in trial 1 is 7.1 times 10, 7.14 times 10 to the negative 4th over 3.57 times 10 to the negative 4th. And then the concentration of C is 0.4 to the x over 0.1 to the x in trial 5. So here we've got 2 equals 4 to the x power. And that's a square root. So my exponent here is actually a 1/2, and we're allowed to do that. It's a 1/2 exponent. So my generic rate law is going to have an 1/2 exponent for C. So I'll just go ahead and write that up top. C to the 1/2 power. In order to find D, we need to compare trials 2 and 3. So for trials 2 and 3, C is constant, 1 to 1, 0.1 to 0.1. E is constant, 0.2 to 0.2. And this one's difficult as well. It's going from 0.2 to 0.5, which is 2.5 times bigger. But look at the rate. The rate is not changing at all. So what exponent am I going to say 2.5 to the x power? What exponent is going to make this change? Just the rate law stay a 1-to-1 ratio. It's 4.55 over 4.55. And this is our first example here of a zero order reaction, because anything to the zero order is 1. So it looks complicated, but if the rate law is not changing, that means the speed does not depend on reactant D. Now for E, we need to look at trials 1 and 4. So 1 and 4, I've got C at 0.4 and 0.4. D is 0.3 and 0.3. But actually, it wouldn't matter what D was doing anywhere, because this is not going to affect the rate law. But that's only because we know it's zero order. But then I can get the rate law of E from 1 to 4 is 0.56 to 0.75. And 7.14 times to 1.28 times 10 to the negative 3rd. So this is going to take a little bit of math here as well to look at this one. All right? All right. So again, now I'm looking at rate 4 to 1 for E. So rate 4 over rate 1. And we're only looking at E because everything else is constant. So that's E of trial 4 to the x over E of trial 1 to the x power. So that's going to give me 1.28 times 10 to the negative 3rd over 7.14 times 10 to the negative 4th equals 0.750. Now I'm going to simplify this in case some of you have been missing it. 0.560. When those are both to the same exponent, I can just make this whole big thing to that exponent there, and it simplifies my math a little bit. And this is going to give me a 1.79 equals 1.34 to the x power. So how in the world do we solve for that one? Because that doesn't simplify very simple. So what we need to do is to do a logarithm. Now, there's lots of ways. Some of you guys know how to do this, some of you don't, so I'm just going to work through a way to do this. If we did log of 1.79, what that's going to do is move the exponent out front, is going to equal x times the log of 1.34. There's other ways to do this, but this is one of the easier ones if you've never had the logarithms before. And then you can just solve for x, because you can just punch those numbers in your calculator. Log of 1.79, hit enter, divided by log of 1.34, hit enter. And you see that this is in fact a squared relationship. Even though it's not that visible, E is a squared relationship. So when all is said and done, I get a rate law there. If we went through everything, rate equals K, C is to the 1/2 order, D is 0 order, and E is a squared relationship. So there is my rate law. We had to go through all of that just to get to all of those, what are the exponents for each individual species. This is probably the hardest example you're going to see. You do need to know how to work out some of this math. There is a simple logarithm there to solve for the exponent. If that's new to you, please pay attention. And then we could take any of those trials to solve for K and their units. You just plug them in and solve for K. And now that you know the rate law and K, then you can apply it to any. So let's go through K again. How do we get the units on K? Well, my rate law is always going to have units of moles per liter per second, or per time. It could be minutes too. You got to be careful for that. And K is always going to be an unknown. But all the other molarities here, this is molarity, moles per liter, moles per liter, moles per liter. The overall order, which is represented by the variable n again, so now it means shells and moles, and in the context of kinetics, it means order. That's a 7th order reaction. Okay, so this is moles to the 7th power over liters to the 7th power. So I need K to cancel out all of these moles except for one, and I need K to be a function of time. So in order to do that and leave my moles per liter per second out of this, K is always going to cancel out inverted, cancel out all but one of those. So I need liters to the 6th, moles to the 6th, and that'll cancel out all of that, and the 7th will cancel out those 6, and I'm left with moles per liter. And then K is also going to need seconds in there. So now I'm left with moles per liter per second. So the generic construct for K, the units of K, if you know the overall order, it's going to be liters to the order minus 1, because we need to cancel out all but one of them, moles to the order minus 1 per second. And I say seconds casually because that could be minutes as well, or hours, or whatever the speed is in. But this is a generic formula to help you calculate the units on any value of K. Invert the reaction order and subtract 1, because you need to cancel out all but one of them to leave moles per liter per second on the other side.